Hello. I'm going to present on the technology for the facial recognition. Um, I am Seung Lee.
Japanese class that I learned. So then, don't take off your interpreter. Yeah. I will tell you about the mobile face recognition from engine to line developer day. This is the content that I prepared. First, we will see about the face recognition, and second is about face engine that we made, and third, engine to product called face sign, and we will review these contents. The first is about the face recognition. In elevator, we use face recognition replace the authentication. So normally when we enter the elevator and tagging their cards and put their cards back and choose the floor. But with the face recognition, they enter the elevator and recognize their face and choose floor. And in vending machine, face recognition replace the payment. Normally we take card or cash to pay, but with face recognition, we choose the product and face recognize and then get the product. In this flow, the different from the elevator is we sometimes use second verification if needed because it replaces the payment. So wrapping up all of those flows, we simplify UX using face recognition, and sometimes we insert the second verification flow when result is risky. So with this face recognition, we decided to make it to in check-in system. Normally, check-in system have two goals, two problems, like long lines of developers waiting to see keynotes, and personal information verification process by email and name. So the Ryan developer day whole process is like below. First, we register in online and line up and check personal information and get goods and watch session. There is a bottlenecks in lineup and check personal information. But with face recognition, we can reduce the bottlenecks in lineup. We can reduce the reduction of waiting time with less than 1 second recognition speed and remove process to verify name or personal information. I always present about this AI to product, but I also get the question like, can AI solve all problems using only model? And I always say never, never, never. So I will share experience about engineering in the engine and engineering in the service. First is about the face engine. In image, we get detect in the image, like face is detected in the image and align our face and we warp to the canonical face and extract the features from our image. After we extract our features, we find person who is in gallery set using face features, not face image. Using nearest neighbor retriever and identify via simple thresholding. Applying face recognition to service, we focused on 4 parts, choosing deep learning framework like TensorFlow or CoML, and functions like detect, alignment, recognition, and MLKit and iOS Vision framework support this function. And we also have to consider supporting multi-platform like iOS, Android, macOS, Windows, and Linux. And we also can't lose the high accuracy and fast speed, like 99% accuracy and 0.1 second speed. So we made our engine. We support multi-platform and constructed with floating point 32 and int 8 based on CPU. And front end, we support C++ front end, Python front end, and other things. And we also have a bunch of functions. This is the full flow of face engine. We got high resolution image from the device and resize it to the low resolution image for engine and detect and tracking our face and align our face, recognize, and after post-processing, we get human information from our image. So I will share the optimization experience in face engine. First is about the lightweight model for high accuracy and fast, and inference engine optimization for more speed, and layer optimization for more and more speed, and I also got some bonus point. First is about the lightweight model. We focus on green square part which placed in left top corner. We knew then that the greater the number of operations, the higher the accuracy. But we have to learn the model in the device. So we have to get really small operator and get really high accuracy. So I said trade-off of accuracy and speed, but we don't trade off. In general, what we call the real-time model in the paper is model based on GPU. Can we use a GPU-based model on an iPad or a real-time device that you guys use to face check-in? I think it's really hard. So we targeted CPU-based model, and the first model is face detector that I showed. PILI model, which generally used in paper, is really have high latency and model size, and our model size is really small, and we can use it in CPU. So our standard is real-time in mobile CPU environment. Also, using the CPU can give the users the opportunity to use the GPU for stickers or 3D graphic rendering. We draw ROC curve in FDDB dataset. Normally placed in upper left is good model. Compared to face boxes lightweight detector models, the model size is about 10 times smaller while providing nearly the same level of accuracy. Our original model is good in mean-squared error too. Facial landmark detector placed in good length, but it's a bit burdensome to learn a model with this model because latency is quite high, like 1.2 seconds, and model size is above 90 megabytes. So we solved this problem with knowledge distillation method. After we use this method, 46 times reduction in latency and 200 times reduction in model size. I think this is enough to run the model on mobile. Last is about the face recognizer. I think our baseline model is in competitive position. Our baseline model is mobile FaceNet. So we saw three parts, and running the model on the engine requires a lot of optimization. But we have tabulated it to know what to focus on. Convolution is the most common because it's a neural network. So we focus on optimizing convolution layer. Also, convolution depth-wise in face recognizer have 14%, so we also focused on that part too. So second is about inference engine optimization. There are many known ways to optimize. One of them is depth-wise separable convolution. Depth-wise separable convolution splits the layer into two steps. Let's see how it works if you split in two steps. Convolution, we use 3 by 3 convolution and get input 16 input channel and output 16 channel. So we multiply all in just convolution, but with depth-wise separable convolution, we multiply the input channel and the 3 by 3 depth-wise, but add the 1 by 1 point-wise convolution. So total parameter is quite different with the convolution layer. In theory, you can see that the amount of computation is about twice less for depth-wise separable convolution. But if you actually use it on the engine, make sure to test it. After we test the PyTorch and TensorFlow 2.0 model, we can show that the speed is quite different from the theory. In case of PyTorch and TensorFlow model, convolution is faster than the depth-wise separable convolution, even though parameter is big. So we knew that fewer parameters and less computation doesn't mean faster speed. However, in our engine, depth-wise separable convolution is faster than convolution, so we use it. Please check the method in client device before you applying in the product. We mainly focus on iOS and Android and CPU. Third is about layer optimization. There are three ways to implement this convolution. First is about the for loop, direct convolution. And second is matrix multiplication like gem method and Vinograd convolution. General methods to develop is just using for loop. We simply implemented overlapping multiple for loops. To make speed faster, we sometimes use the SIMD operation provided by Intel or AMD, such as AVX or Neon. And second, gem-based convolution. In the gem method, the weight and feature map can be extended and calculated at once. GEM is divided into chunk units optimized for each factor. If you operate it in chunks like this, it uses less memory and can be used easily in mobile. Last is about Winograd convolution. In the case of 3 by 3 convolution, there's a way to calculate by converting multiplication to multiplication and addition mathematically. This will make less computation than before. So we saw the 3 convolution layer: direct convolution, gem-based convolution, and Winograd convolution. Which layer should we use? So we compare all of those things. Since there are intersections in the graph, like that part, we should only use it if we met certain condition. Like in case of channel is above 16 and width and height is between 16 and 128, using Winograd convolution is faster than convolution. In 3 by 3 convolution, in case of width and height is above 8, using gem-based convolution is faster than convolution in CPU model. And last is about 1 by 1 convolution. We compare direct convolution and gem-based convolution. In case of channel is above 64, using gem-based convolution is faster than convolution. So we compare those layers and optimize which is the best in the case. After we applying this case, we get 1.3 times faster in iPhone and 2.7 times faster in CPU and 1.2 times faster in Android. It's quite a bit, performance is better than before. So other thing is batch normal folding. There are many cases where batch normal comes after convolution, in which case it is possible to combine them into one layer. If a convolution is followed by an X like ReLU, it can be merged together. So we call it layer fusion. After recombining these layers, we also get some speed improvement in iOS, Android, and CPU, like 1.1 times faster and 1.0 times faster and 1.19 times faster. It is, I think it is, you can think it is really small value, but for the recognition speed, it is like huge value. This is the bonus that I made. In the face detector paper, there is a hidden layer that is not included in the speed measurement index. NMS top K role is to find an algorithm that finds the most accurate box in the model's boxes, which increases the cost of the sorting by the number of boxes. The rest square box we generally use in paper, we don't think to change the config value. However, if you change NMS top K value to 5,000 to 1250, the speed becomes 6 times faster than before. So little difference in accuracy, but it is really reasonable because accuracy is 0.009 is different, but speed is 6 times faster than before, 2.6 times faster in CPU, and 2.4 times faster in Android. So also there's a space for speed improvement even at floating point. Floating point that we know is constructed with one bit for sign bit and 8 bit for exponent bit and 23 bit in fraction bit. Also, floating point is promised to be expressed in an implicitly normalized format. That's why there are special cases like 0, none, and important denormalized numbers came. We focused on denormalized numbers. Recently, we found that different chipsets handle the denormalized numbers differently. So in our model, looking at the weight of the model, there were a lot of subnormal values, like exponent values is in there. So we get some experiment. Is floating point operation slow if there is a subnormal value in the chipset of a specific device? Yes, it makes some slow in our model. So we decided to change it to normalized number. this value is eventually close to 0, the method we can take is to replace the subnormal number with the number of normalized expression. This is the code that we converted the normalized number to normalized expression. After we applying this floating point change, this makes some speed improvements too. After replacing this value, the accuracy of the model was not affected, but however, the speed is 5 times faster than before, so it's like a huge difference. This is all about the engine that we made and optimized. After we optimized our engine, I decided to make this engine to product. This session is quite easier than before, so relax. Making a product for the first time has to go through a huge trial and error. Let's imagine that we developed a line application. Developer, planner, and designer work together with great UI and UX can make application. How about face sign application? With all these members together, we don't know which UX should be used in AI product. Let's see how we solve this problem. This is the flow chart. Face engine is constructed with 3 parts that I tell you before: recognize face and alignment our face and recognize who he was. And nobody gave me the image, so I used my face as a demo image. My image will continue to be appeared. I plan to apply these 3 functions to product. With online registration, speed is not a big deal than recognition. I focused on accurate face data in registration than you did in online website. And in recognition, I focused on speed which you saw in line developer day entrance. Last, we can recognize in client, but we decided to use recognition in server because of accuracy. Because we use servers in recognition, we also have to consider seamless interact between server and client. I will mainly introduce the way to optimize in client part. The reason I decided to introduce only client part was on registration, we just handle one static image that you registered, but on recognition, we have to handle dynamic frame to get best accurate face data. We don't make device tilde and type slides because they are not related with development. This is what I did for before recognizing and after recognizing the face. We did device tilde, type, and frame processing and pre-process for UX design and development. And after that, face size and face alignment, network, and frame processing and post-processing UX design and development. For device tilt, we made device to have more than 70-degree angle because of recognition that you saw in line entrance. We also choose iPad because of widescreen. This is about the frame handling. Engineering in AI consults a lot of papers and OpenCV. Due to the lack of relevant data, we often refer to papers or OpenCV to implement our own algorithm. So with this image, we change it to the vector size and multiply with the Laplacian kernel and get the value like 64 for the blurry image and 1000 value in the not blurry image. So we can discriminate which is blurry or not. Also, we also consider gyroscope, which involved in iPad is also used to compensate if the device is shaking. At first, I thought horizontal design was more appropriate. After receiving feedback from the user, showing the recognized picture felt uneasy and felt anxious for the user as if not saving. So we changed our design to vertical, and it gave us reduced eye strain. First time, they have to see their recognized face and their name and email and the button on the right bottom corner. But we changed the design and they just see their name and the button. And I don't have many time to change it to Korean to Japanese. So please be considerate. Yeah. There was some feedback that users didn't know what the device was doing at the first field test. So we start identity at the first time. This is the identity that we made in debut, and this is my face. Since there is no guide, the user did not know how to act. So we put face guideline in application. After we did all for the before recognize, and this is the flow that after we got some face. The recognizable image size by the engine is much smaller than the actual camera image size, as you can see. It is really small. It was so small that even users who did not intend to use face sign tended to be recognized. So we limit the size of face. Even if the face is too big to go beyond the screen size, the face data may be inaccurate, so we limit the case too. Cut face is same reason that we limit the big face. And the case of recognizing multiple people was the most careful part of us. The second picture was a perceived case as we intended. And third image, we couldn't judge which person to recognize because they have same person image. So we make the line for the solo line. Last image, I decided to recognize a person with a bigger face. One problem could not be compensated if the face of the person behind was larger than the person in front. So we created a guideline to separate people as far as possible for those who are using or waiting. After we consider about the face size, we consider face status. When a person comes to recognize too quickly, we can't get accurate data, so we implemented a new algorithm. The reason why it couldn't be prevented by the Laplacian method was that it needed to be implemented because the background remains the same and only the face moves. At first, I thought that the position of face recognition was right in the center. But through field tests, there was no difference in the time required for recognition to be recognized anywhere, and there was no difference in accuracy. So we recognize all the position in our iPad. The reason for displaying the triangle is that most faces are recognized when the face is turned below 45 degrees. If the face angle is above 45 degrees, the face cannot be seen, so accurate face data cannot be guaranteed. We use Euler angle to implement this function. And after drawing a line from the center of both eyes, I could compare how the face was tilted against the box on the face. So this is the code that we made. And after we implement this algorithm, we can detect the left tilt and right tilt. We also even check when users close their eyes. Since people don't always close their eyes while walking, we recognize the frame with eyes opened. The paper said that the comparison should be made with the vertical and horizontal size of the eyes, but the reality was a little bit different. The table says that 0.25 is the value that when person is not close their eyes, and almost 0.1 value is like they close their eye. But on average, Asian eyes were a little smaller than Western eyes, so paper's value is not affected for me. So it is really making us harder to detect eye movement. We try to find the optimal value for Asians and by testing. Using biometric information for authentication is a very sensitive issue, so we paid more attention to encryption. First, we encrypt the recognized face, and we also encrypt the face features, and encrypt the network size, and encrypt the result. So we did 4 times encryption. It can be difficult to get the best result from a single server results because we use dynamic frame, so we've got the best results from multiple requests. For multiple requests, the requests have to be applied. Is the result more accurate than the threshold value? And is the recognized person same? Or is the detected result encrypted? And more. The pixels of recent cameras are much larger than I thought. So for camera's image, it's like 3 megabytes. We transform it to the smallest size that the engine could recognize, like 100 kilobytes. Finally, the face features were compressed and transformed into smaller binary size to minimize network uses. Through this optimization, it is the recognition speed that was carried out at the Korean Balance Festival 2019. He's the chief of the global AI, and yeah. Since the end of the debut, which held in South Korea, we have continued to study and change the facial features to binary, 15 times, resulting in an average of about 1.6 times faster than before, just for changing uint 8 array to binary. And also, in addition to converting the data to binary, we reduced the binary size once more with gzip compression. There is time to decompress on the client and server, but we adopted this method because total time has decreased and the binary size is decreased too. So it takes 1.6 times faster than before in latency and the total binary size. After implementing everything, we had to induce user action. We designed the UX to get closure when the user is far away and to look at the front when the head is turned sideways. Sorry for the Korean. They said turn right and recognize the face. It's all my image. First, we also created a button to allow the users to check in that you saw before. Someone clicked the button, but someone's not. We think that users have to touch the button because we give them goods. But after we got 100% accuracy of 1,000 people, we decided to let the button disappear automatically. So users don't have to see two scenes. This is the two scenes that we did before, but we merged it together to one scene. In conclusion, when the users enter the conference hall with their face, the users can enter the event hall without a single button touch. And also, they don't have to get their QR code or their device. I've talked about the parts that I set randomly, and these random values are all values we found through trial and error. Also, if there is a problem, the interface is implemented so that it can be fixed immediately. We focused on three parts: face-related setting, and network-related setting, and process-related setting. In Line Developer Day 2, I have this setting too. If you click the logo of our device, you can see this setting too, but don't click it. Don't click it, yeah. We look at the engineering in the engine and service part, and I like to review all of them. In lightweight model, we try different ways to make model lighter and accurate and faster, like knowledge distillation, neural architecture, and etc. and etc. And in engine optimization, we try the following methods to speed up the engine. And in optimization, we try to reduce it even further by 1 millisecond because it is really huge difference in recognition speed. In service optimization, we did for before recognize called detect pre-processing and landmark post-processing. The service was made to make the UX more convenient to users by developing it before and after recognizing the user. So mobile AI in production, we did not succeed in the service in one attempt. There were 5 official listings that we did, but at least 10 times have allowed facial recognition to be presented at this Line Developer Day 2019. First is July, we did in Tech Talk in Naver and Internet Cafe also in Naver, but Balance Festival, which held in South Korea, we did it in COEX and also in Debut, and now Line Developer Day. Many tests don't complete with just one flow. We always have to consider different flow. In order to reduce one button, the exponent's effort was involved and repeated attempts has to be made. The network situation in the field is also important. In order to make 0.1 second speed face recognition, we tested in the fields to ensure stability. So I sit down in the South Korea COEX called COEX, and we check the network latency and the speed. So we think the goal of AI, combining development in the engine and development in the service, our team thinks this is what we have to achieve with artificial intelligence. I conclude this presentation by wanting the users to feel convenient with face sign and to ensure users to say wow. Thank you for my presentation. ありがとうございます。감사합니다.